In the silent vacuum of space, nearly 13 billion light-years from Earth, something impossible glimmers back at us. The James Webb Space Telescope has peered deeper into the cosmic abyss than any instrument before it, and what it's finding defies every law of physics we thought we understood. We're seeing ancient galaxies that shouldn't exist, black holes that appear older than time itself, and cosmic anomalies screaming across the void, challenging the very chronology of creation. These discoveries aren't just bending the rules of cosmology, they're shattering them. Prepare yourselves. What comes next will forever change how we see reality. We begin. For generations, we believed we had a solid grasp on the universe's story. The Big Bang marked the beginning of time 13.8 billion years ago, an epic birth of all matter, space, and time itself. From that primordial moment, everything was thought to unfold in a predictable sequence. The universe expanded, cooled, stars ignited, galaxies formed, and cosmic structures evolved in stepwise fashion. Our cosmological models, built from Einstein's relativity, Hubble's observations, and precision measurements of ancient light, painted a coherent history from the Big Bang to now. We treated the Big Bang as an unquestionable foundation, the starting gun of reality. But what if that foundation is cracking? What if the universe has been hiding secrets that reframe its very origin? In recent years, a string of disturbing discoveries has emerged, each a puzzle piece that doesn't fit our cosmic jigsaw. The more we observe with powerful new tools like the James Webb Space Telescope, JWST, the more the universe seems to whisper that something is terribly wrong with our understanding. Our cosmic timeline, from the first atoms to the first galaxies, might be flawed or incomplete. Picture a grand tapestry of time. Now imagine loose threads appearing, threatening to unravel the entire story. That's where we find ourselves, confronted with evidence that suggests stars, galaxies, even entire structures might have formed too early, too quickly, or in defiance of the physical laws as we know them. It all starts with a seemingly straightforward question: how fast is the universe expanding? The answer turns out to be anything but straightforward. As we'll see, measuring the expansion led scientists to a cosmic contradiction that shook them to the core, hinting that we might have miscalculated the universe's age or missed a fundamental new force of nature. From there, the anomalies only multiply. JWST has spotted galaxies so massive and mature in the cosmic dawn that they should not exist given the youth of the universe at that time. It has detected quasars, the beacons of supermassive black holes, shining when they have no right to be so big so early. And even here at home, astronomers have found ancient stars that seemed older than the universe itself. Each of these discoveries is a paradox. Each forces us to ask, have we misunderstood the cosmic clock? Could something, or someone, have pressed fast forward on parts of the universe? Or are we missing entire chapters of cosmic history? In the following chapters, we'll delve into these mysteries one by one. From the Hubble tension that hints at unseen physics stretching space to the impossible galaxies JWST found at the edge of time. We'll meet stars so ancient and speedy that they challenge the rules of astrophysics. We'll explore the concept of primordial stars, the very first to ignite after the Big Bang, and even entertain radical theories like dark stars powered by dark matter, which may rewrite the origin story of galaxies. All along, the tone will be one of eerie wonder, a calm journey to the brink of knowledge where awe and dread commingle. Because as we uncover these truths, one unsettling theme emerges. Perhaps we are not the first cosmic civilization, in the sense that perhaps our known universe isn't the first iteration of existence. Perhaps traces of an earlier reality or a deeper physics are bleeding into ours. It sounds outrageous. It feels like science fiction. But every anomaly we're about to discuss comes from real data, real peer-reviewed research, NASA or ESA missions, and the finest telescopes ever built. We're going to mix the known science with carefully considered speculation, the kind that keeps scientists up at night. By the end, you may find yourself questioning whether the Big Bang was truly the beginning, or just the latest chapter in a much longer story. So strap in as we journey through the mysteries. This isn't just astronomy, it's a reality check on our most cherished cosmic assumptions. And if even one of these anomalies holds the key to a new truth, we may have to rewrite everything from the age of the universe to the fate of the cosmos. The lights are dimming. The stars are aligning in impossible ways. This shouldn't be happening, and yet it is. The Hubble tension, a cosmic contradiction. For decades, measuring the expansion rate of the universe was like assembling a cosmic puzzle. Using the Hubble Space Telescope, astronomers painstakingly built a cosmic distance ladder, using variable stars and supernova as rungs to measure how fast galaxies are receding from us. They arrived at a number for the Hubble constant, which, in turn, tells us the universe's age. Separately, cosmologists studying the afterglow of the Big Bang, the cosmic microwave background, CMB, with missions like Planck, predicted a slightly different expansion rate based on the early universe's conditions. In principle, the two methods, one looking at the local universe, one at the very early universe, should converge on the same answer. They didn't. There was a hint of disagreement, small at first, but persistent. Over time, that hint grew into a glaring discrepancy known as the Hubble tension. At first, many scientists hoped it was a fluke. Maybe the Hubble telescope's measurements were off by a bit. Say, dust obscured some stars, or crowding in distant galaxies made the readings tricky. Alternatively, perhaps the CMB analysis had unknown systematics. But one by one, those possibilities have been ruled out. And in 2023, the James Webb Space Telescope delivered what many consider the final nail in the coffin of the simple solution. Webb joined forces with Hubble to measure distant Cepheid variable stars, those milepost yardstick stars, in several galaxies with unprecedented precision. The result? Webb's infrared vision confirmed Hubble's measurements to high confidence, erasing any doubt that the local expansion rate is what Hubble said it is. In other words, the Hubble tension is real, not an artifact of error, but a genuine cosmic mystery. The spiral galaxy NGC 5468, about 130 million light-years away, was observed by both Hubble and Webb to calibrate Cepheid stars, critical mileposts for measuring cosmic expansion. Webb's sharp infrared eyes confirmed Hubble's measurements were accurate, ruling out errors and solidifying the Hubble tension puzzle. Let's put this in perspective. Imagine you have two very precise clocks that should agree, but one clock says it's 13.8 billion years since the universe began, while the other, looking at the same universe in a different way, implies it should be several hundred million years younger. That's essentially what we have. Webb's confirmation of Hubble's expansion rate means that when we extrapolate that rate backwards, we get a universe about 13.8 billion years old. But the Planck satellite's data from the early universe, extrapolated forward, gives a slower expansion and thus an older age, around 13.8, maybe up to 14.1 billion years. The gap isn't huge, on the order of 5 to 10%, but it's far beyond the tiny error margins of each method. It's as if one measurement says the cosmos is expanding uniformly, and another whispers that something changed over time, perhaps an unknown twist in the cosmic story. How can the universe be expanding at two different rates? Think of a child's balloon with a grid drawn on it. In normal physics, if you inflate the balloon, every part stretches uniformly. Every grid square grows at the same pace. Now imagine if you noticed the top half of the balloon's grid stretching twice as fast as the bottom half. Impossible? It should be. The laws of physics demand uniform expansion across the balloon's surface. Yet our universe, our balloon of space, appears to have such a dichotomy. The local universe, the part we measure with Cepheid stars and supernovae, is expanding significantly faster than the early universe, the part imprinted in the CMB, would suggest. This isn't a mild discrepancy, it's a gaping chasm that shakes the foundations of cosmology. One physicist described it as measuring the top half of space stretching faster than the bottom, a scenario so strange it should be impossible by our current understanding of gravity. Scientists have tossed and turned over possible explanations. Could there be an unknown form of energy or matter affecting different eras of cosmic time unevenly? We already know about dark energy, the mysterious force accelerating cosmic expansion. But dark energy in our standard model acts uniformly everywhere, like a smooth pressure. What if, instead, dark energy itself evolves or has spatial variations? Some regions of space might be expanding faster than others, essentially tearing the fabric of reality in unexpected ways. It sounds like science fiction, but that's literally one interpretation. Maybe an exotic new phenomenon, call it a anisotropic expansion or a wrinkle in dark energy's behavior. Another proposal, perhaps an early era of physics, like a new particle or interaction in the first few 100,000 years after the Big Bang, skewed the CMB-based predictions. If that's true, it means new physics beyond the standard model of cosmology, maybe a heavier neutrino or a peculiar self-interaction of dark matter or something truly exotic injected into the universe's first moments. In essence, the early universe clock would have ticked differently than we assume. The situation has become so perplexing that Nobel laureate Adam Rees, one of the leaders in measuring the expansion, said, "With measurement errors negated, what remains is the real and exciting possibility that we have misunderstood the universe." In scientific terms, exciting is often code for "we might have something fundamentally new here." But Rees himself admitted the word exciting feels wrong, because if we have misunderstood something so basic as how fast space grows, then all our calculations about the universe's age, size, and fate are now suspect. It's as though a linchpin of the cosmic story is loose. If the expansion rate is not one thing, but two things, or something that changed in an unknown way, then when exactly did our cosmic clock start, and when does it stop? To put it bluntly, either our cosmology models are broken or there's an unknown X factor actively warping the expansion. Neither option is comforting. If the models are broken, we're in the dark, pun intended, about something as fundamental as the age of the universe. If an unknown force is at work, it could imply the presence of a new field or substance in the universe, something woven into space-time that we have yet to identify. We might be dealing with a cosmic chameleon that speeds up expansion regionally or temporally, or perhaps a subtle alteration of gravity on the largest scales. Some scientists have whimsically called this the something big, as in something big is missing in our understanding. Others more dramatically say it feels like reality itself might be ripping at the seams. What's truly unnerving is that Webb's ultra-precise data removed our last comfort blanket, the hope that it was just a measurement error. Now, both the telescope and Hubble are detecting the same impossible contradiction in expansion. We have on one shore the solid anchor of local measurements. On the opposite shore, the early universe anchor from Planck, and nothing in between to reconcile them. We need to find out if we are missing something on how to connect the beginning of the universe and the present day, Rees observed. It's as if we have the origin and the end point of a great river measured, but the flow in the middle is uncharted and wild. This Hubble tension is more than a technical debate, it's a potential omen. If the universe's expansion can pull off this trick, what else might we be getting wrong? One implication hits directly at the Big Bang's legacy. Maybe the universe is actually a bit older than 13.8 billion years, or the Big Bang model needs an extra twist. After all, the age estimate comes from the expansion rate. A faster expansion today could mean a shorter time since everything was closer together, unless something altered the expansion history. So, is it possible the universe is older than we think? or that it went through an unexpected phase, a second acceleration early on, an early burst of dark energy that changed the timeline? We don't have a solution yet. New telescopes are planned, like the Nancy Grace Roman telescope and others, to map expansion in the in-between period and perhaps see the transition. But at this point, many scientists quietly agree some new physics might be required. It's as if we've opened a door to a dark room in the house of cosmology, and we can sense something there but can't yet see its shape. Whether it's a new particle, a new force, or a radical rethink of cosmic history, the Hubble tension tells us the universe's story might have a hidden chapter. This discovery alone, a universe that appears inconsistent with itself, would be enough to send cosmologists reeling. It suggests our cosmic age may be not as ironclad as we believed. But unbelievably, this was just the opening act. Webb was only getting started in upending cosmology. The expansion crisis lit the first warning beacon. Reality might be stranger than our equations. Next came the flood of data from Webb's deep observations, and with it, a series of cosmic revelations that would make the Hubble tension look, in retrospect, like the tip of a very large iceberg. Because if you think a two-phased expansion rate is weird, wait until you hear what Webb saw when it stared into the cosmic dawn. But what Webb found next was worse. Colossal galaxies at cosmic dawn. This shouldn't exist. Not long after James Webb began collecting data in mid-2022, astronomers pointed its golden eye toward a patch of sky near the Big Dipper. They expected, at best, to find a sprinkle of tiny, dim protogalaxies, the cosmic toddlers of the early universe just learning to shine. Instead, Webb discovered monsters. 6 galactic giants emerged from that empty darkness, so massive and developed that they defy explanation. These galaxies aren't just marginally unexpected, they threaten to rewrite the laws of galactic evolution. As one stunned researcher put it, they are universe breakers. Here's why this discovery sent scientists into a frenzy. These 6 candidate galaxies are observed at a time when the universe was only 500 to 700 million years old. That's roughly 3 to 5% of its current age. In human terms, if the universe is a 100-year-old person, we're looking at it as an infant of 3 to 5 years. Yet, each of these galaxies already contains hundreds of billions of stars worth of mass. One of them might weigh in at 100 billion times the mass of our Sun in stars alone, as much as our entire Milky Way, which took over 13 billion years to grow. Another comparison: the Milky Way forms a few new stars per year nowadays. To build up a similar mass in only 500 million years, those infant galaxies would have to crank out hundreds of stars per year, every year, from the moment they formed. It's like finding a 5-year-old child who's 6 feet tall and has the musculature of a bodybuilder. You just don't expect that level of development so early. You shouldn't have had time to make things that big so fast, said Professor Erica Nelson, a co-author of the study. It's just crazy that these things seem to exist. JWST's first deep field, SMACS 0723, a tiny patch of sky seen in infrared revealing thousands of galaxies. Such deep images have unveiled surprises. Numerous, bright, well-formed galaxies in the early universe that conventional models struggle to explain. Some of these may be the universe breakers, massive galaxies observed when the cosmos was only a few 100 million years old, challenging our theories of galaxy formation. To illustrate the absurdity, one astronomer said it's like trying to grow a full-sized oak tree in just 3 months. Normally, an oak takes decades to mature. Likewise, large galaxies were expected to slowly assemble over billions of years by merging smaller ones and forming stars gradually. But these 6 galaxies fast-tracked their evolution on impossible timescales. They somehow skipped the awkward toddler phase and went straight to adulthood while the universe was still in its infancy. The discovery was almost accidental. Dr. Erica Nelson was poring over Webb's deep field images, essentially small cutouts of the sky, when she noticed several fuzzy red dots that were far brighter than they had any right to be. In astronomy, red usually means distant and old. Light from very far away objects gets stretched, red-shifted. By the time it reaches us, it's shifted to infrared. These dots were extremely red and unusually bright. Webb's sensitive infrared detectors had resolved these objects, and initial calculations showed they were likely very distant, redshift Z 7 to 10. When scientists estimated their masses and ages, the real shock came. Each of these galaxies might harbor the mass of tens to 100 billion suns and stars, and they appeared to have already been shining for some hundreds of millions of years by the time we see them, meaning they formed even earlier. How in the universe did these galaxies gather so many stars so quickly? That's the golden question. By the standard model, in the early universe, say 500 million years post-Big Bang, matter was just beginning to coalesce into small galaxies. Those should be tiny dwarfs, maybe 1,000 times less massive than the Milky Way, gradually merging and accreting gas. Instead, we have Goliaths nearly on par with the Milky Way's mass, compressed into a fraction of its size. One is said to be 30 times smaller in radius, despite similar star count. This implies an extraordinarily efficient and prolific star formation episode, or something even stranger, like alternate pathways to pile up mass quickly. We'll explore one such exotic idea, dark stars, later on. The implications are staggering. Joel Reja, a co-author, said, "The revelation that massive galaxy formation began extremely early in the history of the universe upends what many of us thought was settled science." The team nicknamed these objects universe breakers for good reason. If even one of these 6 candidates is truly as massive and old as it appears, our theories of galaxy formation need a serious revision. Perhaps the dark ages of the universe, the period after the Big Bang before the first stars, ended much sooner and with more vigor than we believed. Maybe star formation was like a wildfire in some regions of the early cosmos, lighting up huge swaths of gas in short order. It's important to note that these galaxy candidates are still being studied. There is a chance that some of these red dots could be something other than a galaxy full of normal stars. For instance, one hypothesis was they might be obscured quasars, massive black holes with dusty halos that glow bright in infrared, which could mimic a galaxy's light. If that's the case, the puzzle shifts. It would mean supermassive black holes formed extremely early, another headache we'll come to next. Either outcome, be it lots of stars or a big black hole, is a headache for standard theory. As Dr. Nelson noted, if even one of these objects holds up as a massive early galaxy, it will push against the limits of our understanding of cosmology. The existence of these galaxies forces several possible interpretations, each wild in its own way. One possibility is that the universe somehow made stars incredibly efficiently right after the Big Bang. Perhaps the very first generation of stars, so-called population 3 stars, made of pristine hydrogen and helium, were extremely massive and short-lived, pumping out torrents of new heavy elements and triggering a rapid cascade of star formation. If conditions were just right, maybe a halo of dark matter, the seed of a galaxy, could collapse almost completely in one go, converting its gas into stars in a cosmic blink. This is not how we normally simulate galaxy formation, but nature sometimes finds a shortcut. Another angle, maybe these aren't galaxies in the usual sense at all, but the cores of what will become galaxies, perhaps each harboring an obscenely large black hole or an exotic power source that made them glow super bright. There's speculation, as we'll see, that some early galaxies might have been powered by unusual objects like dark stars or black hole stars. If such things exist, they could produce lots of light and thus make an object look massive without requiring as many normal stars. We'll entertain that shortly. For now, consider the emotional impact on astronomers. The tools built to confirm our theories instead delivered a paradox. It's like planning to meet a baby and finding a full-grown adult in the crib. When Webb spotted those giants at the dawn of time, scientists literally thought this must be a mistake. They double-checked the data, the calculations. Could light from a nearer object be masquerading as a distant one? Unlikely. The redshift was estimated from multiple filters, and follow-up spectroscopies in progress. Each new piece of data so far has only reinforced that these things are really out there and really old. One of the researchers, Ivo Labbé, remarked that the sheer mass of stars in these objects was mind-blowing, and how these monsters fast-track to maturity is unknown. The phrase fast-track to maturity sticks out. Nature, in this case, didn't follow the gradual path we expected. It found a shortcut, or perhaps an alternate route entirely. Perhaps the early universe had pockets of matter so dense that they collapsed into galaxies almost overnight. If such dense regions existed, they might hint at statistical flukes, like 5 sigma density peaks in the random distribution of matter. Very rare, but apparently not impossible if we found 6 in Webb's first small survey. Alternatively, our understanding of how quickly gas can cool and fragment into stars might be incomplete. Could exotic cooling mechanisms, maybe involving primordial molecular hydrogen or even exotic physics, have allowed gas clouds to condense faster than our standard textbooks say? Here's another twist. In one of the new Space Telescope deep fields, the JADE survey for instance, Webb found evidence of evolved chemical elements like oxygen, carbon in galaxies at redshifts above 10. That means those galaxies had already seen a generation of stars live and die, since heavy elements are forged in stars, by 400 million years after the Big Bang. Put together with the universe breakers, this suggests star formation was not only prolific but also quick to enrich the cosmos. The presence of elements like carbon and nitrogen in a galaxy just 280 million years post-Big Bang implies that even earlier generations of stars must have formed and exploded before that time. It's like we're seeing cosmic genealogy and realizing there are ancestors we never expected. Astronomers sometimes comfort themselves by saying, "We must have gotten the initial mass or redshift wrong. Further data will clarify." Indeed, these 6 galaxies await spectroscopic confirmation to nail down their distances and masses precisely. It's ongoing work. But the tantalizing truth is that Webb has already found around 100 other relatively bright high redshift galaxy candidates that weren't predicted by our pre-JWST models. Peter Van Dokkum, an astronomer on one of the survey teams, said, "JWST was not expected to find any galaxies this early. There are roughly 100 more bright early galaxies than expected." This isn't one anomalous observation, it's a pattern. The early universe is littered with surprisingly bright, big galaxies. The cosmic rulebook we wrote over the last few decades, which said the early universe had small proto-galaxies merging slowly, appears to have some missing pages. And as we're about to explore next, galaxies weren't the only overachievers in the early cosmos. Black holes, those bottomless pits of gravity, also seem to have grown up too fast to make sense. In some cases, they appear so early that one must wonder, could they be leftovers from something before the Big Bang? Or did the universe have ways to create giant black holes almost instantly? Our journey into cosmic mystery deepens as we turn to these dark beasts of the early universe. If galaxies are the cosmos's cities, then supermassive black holes are the skyline's towering giants. And JWST has found them in the cosmic cradle, when by rights they should barely exist at all. As astounding as impossible galaxies are, what came next might be even harder to fathom. Black holes that seemingly beat the cosmic clock. Galaxies too big too soon? Next up, black holes older than time? Black holes from a bygone era. Galaxies weren't the only impossible monsters lurking in Webb's early universe data. Scattered among those infant galaxies were signs of something even more enigmatic. supermassive black holes. And not just small ones, but some that rival the mass of those in today's giant galaxies, present when the universe was a mere few 100 million years old. These dark behemoths, which power extremely luminous objects known as quasars, have no business being there so soon. It's as if you walked into a nursery and found not just an adult, but an ancient, wise old sage sitting among infants. For context, a supermassive black hole, SMBH, is a black hole millions to billions of times of mass of the Sun. In the nearby universe, nearly every large galaxy, including our Milky Way, has one in its center, but they grew over billions of years, often by swallowing stars, gas, or merging with other black holes. In the early universe, however, the expectation was that only seed black holes existed, perhaps a few thousand or million solar masses at most, formed from the first massive stars collapsing. To grow from a seed to a billion solar mass colossus in less than 1 billion years is a tall order under standard physics. There's simply not enough time if growth is limited by normal processes. A black hole feeding on gas has a natural speed limit called the Eddington rate. It's like a maximum calorie intake per day for a black hole. Yet, to our astonishment, we found quasars with billion solar mass black holes at redshifts beyond 7, meaning within 700 million years of the Big Bang. Webb's observations have only added to this mystery by possibly uncovering even more of these giants, and even some smaller black holes in unexpected places. One JWST discovery announced in 2023 was the most distant active supermassive black hole known, a black hole in galaxy CERS-109, existing just 570 million years after the Big Bang. Now, this black hole was actually on the lighter side, about 10 million solar masses, only 8 times heavier than the one in our Milky Way center. But that in itself is startling. We're seeing a black hole that formed and grew to millions of solar masses incredibly early. Even more, Webb shook out 2 more black holes in the slightly later universe, about 1 billion years old, that were also on the smaller side. This hints that Webb is sensitive to a population of black holes we couldn't see before, potentially the long-sought seeds of later quasars. It's like finally hearing the whispers of the first black holes. But at the same time, the bright quasars that were known pre-JWST still stand as glaring paradoxes. Telescopes such as Sloan Digital Sky Survey and others had found quasars at redshift 6, 7, even one at 7.5, meaning a black hole of some 1 to 2 billion solar masses was shining when the universe was some 700 million years old. How did it get so big so fast? Traditional growth by accretion, gas falling in, and mergers of smaller black holes struggles to account for it. Even if a black hole ate greedily at the theoretical maximum rate from the moment of the first stars, it's hard to reach billions in 1 gigayear. It's as if we discovered a fire-breathing dragon egg hatched almost immediately after the cosmic dawn when we expected only sparks. Scientists are increasingly considering exotic explanations. One idea is the direct collapse scenario. Instead of a black hole starting as a small remnant of a single star, about 100 solar masses, perhaps under rare conditions, an entire massive gas cloud, tens of thousands of solar masses, could collapse directly into a black hole, skipping the star phase. That would give a head start, a seed of maybe 10 to the 5 or 10 to the 6 solar masses around 100 million years post-Big Bang. From there, reaching a billion by 700 million years is less implausible, though still pushing it. Intriguingly, JWST may have found evidence for such a direct collapse black hole. In one early result, researchers identified a peculiar object that could be a black hole star or a nascent black hole gobbling material extremely early. The term black hole star has been floated for an object that starts as a massive star-like object but immediately forms a black hole at its core powered by infalling matter. basically a star-scale precursor to a supermassive black hole. If JWST saw such an object, it might be catching a black hole in the act of forming in an unusual way. Another radical proposal involves dark matter. Some researchers have suggested that perhaps a fraction of dark matter is not as inert as we think. If a special kind of dark matter particle could clump and cool, it might form dense cores that collapse into black holes. A recent study even posited an ultra-dense dark matter clump scenario, where dark matter interactions lead to quick black hole formation. More exotically, a paper proposed dark stars, not black holes, but giant early stars powered by dark matter annihilation, which could grow to enormous mass, tens of thousands of solar masses, before collapsing into a black hole. If that happened, those black holes would be born big. Think of it as a shortcut, nature circumventing the slow eating process by preparing a massive seed on a platter. In fact, JWST may have spotted candidates for these hypothetical dark stars. A team led by Cosmin Illy and Catherine Fries identified 4 extremely distant JWST sources whose properties match what they expect of supermassive dark stars. Huge, maybe a million solar masses, puffy, hydrogen-helium objects sustained by the heat of dark matter particles annihilating inside them. These objects would shine brightly and could be mistaken for galaxies or quasars. The telltale sign? A particular light absorption signature of helium at 1640 angstroms. Remarkably, one of the JWST objects shows a hint of that signal. It's not definitive, the signal-to-noise is low, but it's tantalizing. It could be the smoking gun of a dark star. If that's true, it's almost too sci-fi to believe. An object powered not by nuclear fusion, but by dark matter itself, something totally outside standard astrophysics. And yet, it would solve 2 puzzles at once. Why those early galaxies are so bright, because a single dark star could mimic a whole galaxy of smaller stars. And where the seeds of big black holes came from, because the dark star eventually collapses into a massive black hole. Mainstream or not, these ideas highlight how desperate and creative scientists have become when confronted with impossible black holes. As one article put it, these early quasars strain our best theories of cosmology. Traditional models just fall short of explaining how black holes could grow so massive so quickly. It's either new physics, dark matter doing something unusual, or unknown processes in star formation, or an overhaul of our timeline. Consider this unsettling possibility. What if some of these black holes formed before the stars, or even before the Big Bang? Could they be relics of a previous universe or a prior phase of collapse? This idea edges into speculative territory, but some cosmologists have pondered whether primordial black holes could form from overdensities in the very early Big Bang, like during inflation. If so, those primordial black holes would essentially predate normal star formation, giving the newborn universe a population of black holes from the get-go. Most would be small, but conceivably some could cluster or merge into larger ones. It's a long-shot theory, but it's interesting that certain mass ranges of primordial black holes have been considered as dark matter candidates too. The presence of massive quasars by redshift 7 already had people thinking about primordial black holes or exotic formation channels. Now, JWST's discovery of a less massive SMBH at Z around 10, the Sears 1011 at 570 million years, suggests black holes were indeed around and growing in the earliest epochs we can see. And if Webb in the coming years finds a quasar at, say, redshift 12 or 15, which is not impossible given its capabilities and the surprises so far, it would really force the question, did these things come from outside the standard narrative of structure formation? From an emotional perspective, seeing a brilliant quasar in the very young universe is awe-inspiring, yet terrifying. These quasars are beacons. We detect them because they outshine entire galaxies with their radiance. To shine so bright, a black hole must feast ferociously on matter falling into it, heating up the infalling gas to incandescent temperatures. It's a display of violent, raw power in the cosmic childhood. It's as if the universe, while still a kid, lit a bunch of nuclear bonfires. We didn't think it had the materials or the time to do that, but it did. One example, ULAS J1342 plus 0928, a quasar discovered a few years ago at Z around 7.54, about 690 million years after the Big Bang, has a black hole of 800 million solar masses. Another, J0313-1806 at Z equals 7.64, just a bit earlier, stunned us with a black hole mass around 1.6 billion solar masses. The team that found it in 2021 said that to reach that mass so fast, it likely had to start as a likely 10,000 solar mass black hole at birth, far larger than any normal star collapse could yield. They suggested a direct collapse scenario as the likely origin. Now, JWST will undoubtedly find more of these, possibly at even higher redshifts, and will gather more data, spectra that show the chemical composition around them, etc. Maybe those data will give away clues, like unusual abundances or temperatures, hinting at the method of formation. One concrete JWST contribution, it can detect the surrounding host galaxies of early quasars better than Hubble could, because of its infrared sensitivity and resolution. Already, JWST observed a quasar at Z around 6 and found it sits in a surprisingly messy, chaotic galaxy merger, which suggests mergers might drive gas into the center to feed the black hole. We may find that many early quasars are in dense environments with lots of fuel. That still leaves the question of the initial seed, though. The overarching sentiment coming from these findings is a mixture of excitement and dread. Excitement, because new physics or astrophysics could be within reach. We might learn something fundamentally new about how the cosmos works. Dread, because it means our current understanding is insufficient. Scientists pride themselves on making predictive models. When observations repeatedly say this shouldn't be possible, yet here it is, it's humbling. It's a reminder that the universe is not obliged to follow the script we wrote for it. From a late science tone perspective, one might say, this is the moment cosmologists realized the universe was far more competent at building things, stars, galaxies, black holes, than we ever imagined. Something was cheating the cosmic timeline. Either nature found clever shortcuts to grow complexity fast, or our concept of time and growth in those epochs is flawed. Let's step back. We now have two major cracks in the standard cosmology. The Hubble tension, the universe's expansion doesn't add up neatly, and the discovery of overmassive early structures, galaxies and black holes far too developed too soon. Each alone is provocative. Together, they paint a picture that perhaps our cosmic timeline is skewed or incomplete. Are we absolutely sure the universe is only 13.8 billion years old? That number is derived assuming our models, like constant dark energy, etc. If something like the Hubble tension forces a change in the model, the age could tweak a bit. Some alternative cosmologies, for example, allow for an older universe, maybe by a couple billion years, say by reducing dark energy or other modifications. That's still not enough to say stars older than the Big Bang, of course. Nothing in physics currently lets you have an object older than the universe, unless our definition of the universe changes. For instance, a cyclic universe where Big Bang is not the beginning but a transition. Could it be that our Big Bang was not the true beginning? If evidence accumulates that some objects seem to predate the Big Bang's timeline, one far-out idea is that the Big Bang might have been a reboot, a transition from a previous cosmos. In some cyclic or ekpyrotic models, the universe bounces, and some structures or conditions could, in principle, carry over. Though it's extremely speculative to say a star or black hole could survive a bounce, likely not, due to infinite densities and so on. More likely is that the Big Bang is fine, but our understanding of what happened right after it is lacking. Perhaps time flowed differently in the very beginning, or some regions evolved faster than others. Not a standard idea, but these anomalies push us to brainstorm such possibilities. Now, before moving on, we should clarify. When we say stars older than the Big Bang, we're channeling the paradox. By definition, nothing can be older than time zero of our universe, unless our concept of time zero is wrong. We've already encountered one star, the so-called Methuselah star, that gave us this very headache. The Methuselah star, older than time? Not all cosmic mysteries lie billions of light-years away. One of them twinkles in our own Milky Way galaxy, a mere 200 light-years from Earth, visible with a good telescope in the constellation Libra. It's cataloged as HD 140283, but it's better known by a nickname that speaks to its legend, the Methuselah star. This unassuming faint star caused a stir because initial estimates suggested it was 14 to 16 billion years old, seemingly older than the universe itself. If that doesn't send a chill down your spine, consider what it meant. Either the star's age was wrong, or the cosmology was wrong, or both. Some wryly asked, did this star precede the Big Bang? HD 140283 is a metal-poor subgiant, meaning it's an old star that has very few elements heavier than helium, metals in astrospeak. That's a clue to its antiquity. Stars that formed later in the universe's history inherit lots of heavy elements forged by previous generations of stars. But this star is almost pristine hydrogen and helium, implying it formed when such heavy elements were rare, near the dawn of star formation in our galaxy. Astronomers have long known it's one of the oldest stars around, but putting a precise number on that age is challenging. It involves stellar evolution models and measurements of the star's brightness, color, and composition. In 2013, using refined data from the Hubble Space Telescope to measure the star's distance and luminosity accurately, a team led by Howard Bond did the most precise age estimate to date. They got 14.5 plus or minus 0.8 billion years. That upper end, 15.3 billion, was obviously in tension with the 13.8 billion year age of the universe. Even the central value, 14.5, was uncomfortably older. Bond was quoted, "At first glance, it's an obvious dilemma. The star appears older than the universe." Indeed, the news headlines at the time were sensational. Star older than the universe? What do you do with a paradox like that? It's like carbon dating a relic and finding it's older than the Earth. One possibility was that stellar physics was slightly off. Maybe the models of how stars age, how they fuse elements and brighten over time, needed tweaking. Another was that perhaps the universe's expansion age had a bit more uncertainty than thought. Back then, the Hubble tension was not resolved, and indeed, earlier estimates of the Hubble constant would have given a universe age of around 12 to 13 billion, making the star's age even more problematic. Or maybe, just maybe, it signaled something fundamentally weird. Could the star have formed in a precursor universe and somehow survive a transition? That last idea was fringe, of course, but it shows where minds wander when confronted with a seeming impossibility. In this case, the resolution was modest and reassuring. The measurements and models were refined to the point that the star's age, with overlap of error bars, just barely fits under the universe's age. The latest estimate puts the Methuselah star at about 14.3 billion years old, with a plus or minus 0.7 billion uncertainty, which makes it younger than 13.8 at the lower end of the range. In other words, the star is likely around 13.7 billion years old, basically as old as star formation could possibly be, forming just a few 100 million years after the Big Bang. So the crisis was mostly resolved by carefully accounting for things like the star's oxygen content, which affects its opacity and hence age estimates, and other factors. The Methuselah star now serves as evidence that our galaxy, or at least the halo of our galaxy, had started forming stars extremely early, not too long after the first galaxies began to take shape. But let's not brush it off too quickly. Imagine how it felt in the interim period when the numbers were really suggesting an impossible age. The ancient halo of the Milky Way is populated by very old stars and globular clusters, dense star clusters. Many of those have ages in the 12 to 13 billion year range. So for a while, we had this nagging worry. What if we've underestimated the universe's age? Could the universe actually be, say, 15 or 16 billion years old, and something in our cosmological parameters is off? After all, the age depends on the expansion rate and composition, Hubble constant, dark matter, dark energy, etc. If, for instance, the Hubble constant were on the low side, like 66 kilometers per second per megaparsec instead of soon 70, and/or dark energy behaved differently, you could squeeze out a bit more age. The Methuselah star's age essentially prodded cosmologists. Are you sure about that 13.8 billion figure? So far, all other evidence, like the CMB, strongly supports soon 13.8 billion years. So the likely truth is the star is at the extreme end of possibilities, but still under that mark. It probably formed as one of the very first stars in the Milky Way's progenitor, maybe in a primeval dwarf galaxy that later merged into the Milky Way's halo. It zooms through our galaxy on a long looping orbit, a visitor from the distant past. In fact, its fast motion across the sky, it's a high-velocity star, is what brought it to attention a century ago. It's moving about 1.3 million miles per hour relative to us, and is on a trajectory that suggests it came from the outer galactic halo. It likely originated in the ancient halo population, those first generations of stars that formed in our galaxy, or smaller galaxies that became our galaxy. From a narrative standpoint, the Methuselah star is like a lonely elder in a galaxy of youngsters, quietly carrying the story of the early universe in its chemical makeup. It has very little iron or heavy elements, about 250 times less iron than the Sun, which tells us it formed before those elements were common, likely before many supernovae had seeded the cosmos with heavy metals. It's basically made of primordial stuff, hydrogen, helium, with just a sprinkle of the first heavy elements. Studying it is like reading a history book written in the star's atmosphere. Now, while this particular paradox, star older than universe, has been mostly resolved, it underscores a theme. Ages in astronomy are tricky and often rest on models. If our models are incomplete, ages can be misestimated. So far, we haven't found any object that absolutely is incontrovertibly older than the universe. That would be the ultimate game changer. But we dance on the edges of that possibility. Every time we find something extremely old, we test the consistency of our cosmic timeline. Globular clusters, for example, were once estimated to be 15 to 18 billion years old back in the early 90s, which was inconsistent with a then 13 to 15 billion year old universe, given the data by Hubble then. That mismatch was resolved by better understanding of stellar physics, like factoring in helium diffusion, updated opacities, etc., which lowered the cluster age estimates, and by realizing the universe was a bit older than some of the lower estimates. The current globular cluster ages are around 13 billion max, aligning nicely. So often, nature has just so timing that everything fits at the limit. But whenever measurements improve, we brace for potential conflicts. Now, combine the Methuselah star story with what JWST is telling us. In our Milky Way, by 13.7 billion years ago, which would be maybe 100 million after Big Bang, a star had formed. In the far universe, by 300 to 500 million after Big Bang, whole galaxies and black holes had formed. It's painting a picture where the cosmic dawn, the era of first stars and galaxies, is extremely early and vigorous. Perhaps the first stars, population 3, formed as early as 100 million years after the Big Bang. That's only 0.7% of the current age of the universe. The universe was still basically an infant, yet starlight may have already flickered on. Let's talk a bit about those population 3 stars as we promised, because they tie in to both the early galaxies and the Methuselah-like old stars. Population 3 refers to the first generation of stars, born from primordial gas with no heavy elements. They've never been observed directly. They likely lived short, died quick, but their existence is a prediction of Big Bang cosmology. They should be what ended the cosmic dark ages. We've been hunting for indirect signs of them. That Space.com article we saw notes JWST found evidence of POP3 stars in a distant galaxy, GN-Z11. They detected a certain signature of ionized helium that suggests very hot, primitive stars. POP3 stars would be extremely hot and massive, thus ionize helium strongly. This is big news. It's not a confirmed individual POP3 star, but it's like smelling smoke and inferring a fire. What were POP3 stars like? Theory says they might have been monsters, perhaps 100 to 300 solar masses each, very bright, very short-lived, a few million years. They would end in giant supernovae or direct collapse to black holes, seeding the first heavy elements or the first black hole seeds. If some of those direct collapse black holes were in the thousands of solar masses, they could indeed be the seeds of the early SMBHs we see. Also, the biggest POP3 stars might even have collapsed without a supernova, so-called pair instability collapse above 250 solar masses, leading to an intermediate mass black hole remnant. So one emerging coherent picture is POP3 stars form early, some die as supernovae, making the first metals, leading to second-gen stars like Methuselah. Others die forming black holes which merge or accrete to become seeds of quasars. Meanwhile, some gas clouds skip straight to black holes, and maybe a few exotic dark stars lurk too. In any case, by the time the universe is 200 to 300 million years old, it might already have a few globular cluster-like clumps of stars and some black holes around 10 to the 10th solar masses. Then, by 500 million, those clumps merged into nascent galaxies, star formation peaks in some, and voila, you get those universe-breaker galaxies and some quasars. This scenario is speculative, but attempts to accommodate what we're seeing. It would require that our models of star formation under pristine conditions are adjusted. Maybe cooling of gas can happen faster via molecular hydrogen or streaming velocities or something. The POP3 era is basically the frontier of time we are now probing with JWST. It's as if we're archaeologists who have dug so deep we're at the bedrock of the first structures. JWST, with a bit of luck, might even catch a supernova from a POP3 star, or a gamma-ray burst from one. Some GRBs have been observed very far, and a certain kind called a POP3 GRB has been theorized. If we ever directly witness one, it would be a direct confirmation of stars almost as old as time. Now, all these findings collectively whisper an intriguing possibility. Could the Big Bang itself be just one frame in a larger movie? The anomalies often make us think of scenarios like, what if there was more time before the Big Bang? Perhaps a slow roll of time we're unaware of, or remnants from a prior contraction. Some cosmologists have conjectured solutions to Hubble tension by saying maybe fundamental constants changed, like speed of light was higher early on. A controversial idea, but not impossible in theory. Or maybe we're in a local bubble with different expansion, less likely. There's also the idea of a multiverse. Could these anomalies be hints that our universe interacted with another? Probably not necessary. We can explain them with new physics within our own universe, but it's evocative to think about. For example, some have speculated an observed cold spot in the CMB might be an imprint of another universe's collision. That's tangential, though, not directly related to stars older than the Big Bang. Let's ground this again. We have not definitively found any object that we can flat out say is older than the Big Bang. What we have are objects that are as old as the Big Bang timeline allows, and they are teaching us that the early universe was astonishingly productive. So perhaps a more accurate rephrasing of stars older than the Big Bang is stars that challenge the Big Bang timeline. It's an alarm bell that maybe the details of the timeline need revision. This is a good moment to reflect on how science progresses. We have a model, Big Bang cosmology with inflation, dark matter, dark energy. It's been wildly successful in many ways. But now cracks, the tension, the early structures, are signaling that either we add new ingredients, like new particle physics, etc., or we adjust the framework. Maybe tweak the nature of dark energy, or allow something like early dark energy injection. It might not mean throwing away the Big Bang, rather enriching it. For instance, one solution for Hubble tension that's been proposed is an episode of early dark energy, essentially a brief extra push of expansion a few 100,000 years after Big Bang, which could reconcile the numbers. That doesn't break Big Bang, it just adds a chapter we didn't know, a kind of mini-inflation later on. Similarly, to get early galaxies, maybe the small-scale power spectrum of matter, the distribution of small-scale fluctuations from inflation, is different than we thought, producing more dense regions that collapse early. That could be another explanation. Maybe inflation, the rapid expansion at the universe's birth, created more abundant high-density fluctuations than standard models assume, leading to more early collapsed objects. This is plausible and is being looked at. If the primordial spectrum has a blue tilt or some features, it could yield many more early structures. All these technical possibilities aside, what stands out is the emotional, philosophical aspect. The universe continually surprises us and forces humility. We thought we were near cosmic enlightenment with a standard model of cosmology locked in. But the JWST age is feeling a bit like the 1920s again, when Edwin Hubble discovered the expansion of the universe, shattering the static universe idea. Or like the 1990s, when we found cosmic acceleration unexpectedly. We're witnessing a potential paradigm shift, or at least a significant paradigm adjustment. Now from gloom to wonder. How amazing is it that we, tiny creatures on a rock, can infer the existence of stars and galaxies billions of years ago, and then get puzzled when they don't fit our mental model? It's testament to human curiosity and ingenuity, and also to the richness of the cosmos. These impossible observations are not failures, they are gifts. They tell us there is more to learn. Come, push further, expand your understanding. One can also feel a sense of dread. If our cosmos is more complicated, then predicting its ultimate fate becomes murkier. If dark energy isn't uniform, could it tear regions apart? A big rip scenario? If black holes were around earlier, could some black holes be artifacts from beyond our universe? Cue speculative horror. A late science narration might go like, either scenario, that our equations are broken or an unknown force is at work, is equally chilling. It means we do not fully grasp the machine that drives reality. As we near the end of our journey, let's recap and see where all this leaves us. We started with a Big Bang and a solid timeline. We encountered a cosmic expansion paradox, the Hubble tension, suggesting something's off in cosmic expansion history. We saw galaxies that grew up too fast, hinting at a very efficient early universe or new physics. We saw black holes that appear far too early, hinting at new formation channels or pre-existing conditions laid by the universe. We met a star in our own galaxy that pushed the age limit, reminding us our local universe holds clues to the dawn of time. We touched on dark stars and primordial stars, wild concepts that just a few years ago might have belonged more to theoretical musing, but now are inching towards plausible given the data. And we haven't even talked about some other oddities, like hypervelocity stars or cosmic microwave anomalies. Those are other tales of strangeness. Speaking of hypervelocity stars, the user prompt did mention them, and they are indeed interesting. Stars flung at such high speeds they escape their galaxies. We should briefly see how they tie in to the cosmic puzzle. It might seem separate, but there is a connection. Hypervelocity stars, especially old ones, could potentially tell us about the history of galactic interactions and dark matter in our galaxy's halo. Let's explore that in the next section, and then come to a grand conclusion of what all these anomalies might mean for the foundations of cosmology. Rogue stars on the run, clues in hypervelocity. While we've been gazing at cosmological distances, one more bizarre phenomenon is happening closer to home. Hypervelocity stars being booted across the galaxy at jaw-dropping speeds. Imagine a star like the Sun suddenly getting kicked so hard that it escapes the Milky Way entirely, hurtling alone into intergalactic space. It sounds like a scene from a cosmic pinball game, but it's real. And it's another case of nature doing something extreme that makes us sit up and take notice. The first hypervelocity star was discovered in 2005. Since then, dozens have been identified. Most of them, as it turns out, are exiles from the Milky Way center. The leading mechanism is pretty well understood. If a binary star system strays too close to the supermassive black hole at our galaxy's core, Sagittarius A star, tidal forces can rip the binary apart. One star gets captured by the black hole, and the other gets flung outward at tremendous velocity, a gravitational slingshot. Think of a doomed dance. Two stars go in, one star comes out like a bat out of hell. Some of these runaways move over 1.5 to 2 million miles per hour, fast enough to escape the galaxy's gravity altogether. The Milky Way's escape velocity out near the Sun is a few hundred kilometers per second. These hypervelocity stars can reach 1,000 plus kilometers per second. Why include these in our discussion of foundational cosmology? On the surface, hypervelocity stars seem more like an astrophysics curiosity, local dynamics, not universe-shaking. But they have a deeper significance. They are probes of our galaxy's gravitational field, which in turn is dominated by dark matter. As one Harvard astronomer, Warren Brown, noted, these unbound stars could reveal the shape of the dark matter distribution surrounding our galaxy. They travel so fast and far that their trajectories trace out the gravitational potential of the Milky Way's halo. If we map their paths by measuring their velocity and direction precisely, we can infer how matter, especially unseen matter, is distributed. In essence, hypervelocity stars are like test particles thrown into the gravitational pool of the galaxy. By observing their motion, we indirectly feel out the contours of that pool. This is important because, recall, dark matter is a huge part of cosmology. It's one of the pillars of the Big Bang model, an invisible mass that shapes galaxies and cosmic structure. Yet we've never directly detected a dark matter particle. Hypervelocity stars give us another handle on dark matter. By measuring enough of them, we can better constrain the mass and shape of the Milky Way's dark matter halo. There have been hints, for example, that some hypervelocity stars might originate from outside the Milky Way, possibly from another galaxy like the Large Magellanic Cloud, meaning they were ejected elsewhere and then fell into our galaxy. If that's true for even a few, it indicates galaxies tossing stars to each other like cosmic spitballs. It's a dynamical dance that in itself is fascinating. One recent study using data from the Gaia spacecraft, which measures star positions and motions with exquisite precision, identified a whole bunch of high-velocity stars. Interestingly, they found many were not coming from the center, the classic SMBH slingshot scenario, but from the disk of the Milky Way. Some possible causes: past supernova explosions kicking companion stars away, or interactions with globular clusters. But about 30% of the fastest seem to have extragalactic origins, possibly stars from another galaxy zipping through. If true, that means the Milky Way has been infected with foreign stars, which might have been accelerated in collisions or by another galaxy's black hole. So hypervelocity stars remind us of the violent side of galaxy evolution. They're literally scars or ejecta from dramatic events. And if a star can be so accelerated, could there be other things flung around? What about hypervelocity globular clusters, or even compact remnants like neutron stars? The latter could tie to cosmology in terms of seeding the intergalactic medium with heavy elements, etc. Bringing it back to our theme, hypervelocity stars don't directly speak to the age of the universe, but they do speak to the dynamical processes that can also affect star formation and survivability. For example, could a star get kicked out of a dense region and survive in intergalactic space for a long time? Possibly. Could such a star be extremely old and wandering between galaxies? There is speculation that the space between galaxies, the intergalactic medium, might host orphan stars, say ripped from galaxies during mergers. If some of those are ancient stars, in principle, they might outlast their original homes. Imagine a star formed in one of the first small galaxies that later got ejected during a merger and has been roaming the cosmos ever since, not bound to any galaxy. That star could truly be almost as old as the universe and isolated. It's poetic, a solitary traveler nearly as old as time itself, drifting in the void. We haven't identified such a specific case, but hypervelocity stars show it's possible for stars to end up in distant exile. Another subtle connection: hypervelocity stars ejected by black holes indirectly confirm the presence of supermassive black holes and their power. We see their effect even if we don't directly image the event. This resonates with the idea that the centers of galaxies and their black holes were very active places, possibly fueling quasar phenomena and such even in smaller proto-galaxies. If hypervelocity stars happen now, they likely happened then too, meaning early galaxies might have also flung out stars or stellar remnants at great speeds. Perhaps some of the earliest generation stars were ejected from their birth galaxies in the chaos of formation and ended up isolated, which could make them effectively fossils for us to find later, though by now they'd be very faint and possibly dead remnants. On the flip side, hypervelocity stars demonstrate extremes of gravitational interaction, which test general relativity in strong fields near the black hole. They turned an abstract prediction, Hill's mechanism, proposed in 1988, into reality. So once again, nature went to the extreme, and it matches our physics, thankfully, in this case. But one wonders, in other galaxies, perhaps even more powerful events might eject stars at fractions of the speed of light. None observed yet, but who knows around a merging black hole or something. In summary, for hypervelocity, it's another piece of the cosmic puzzle that shows the dynamism of the universe. It doesn't overturn cosmology, but it adds depth to our understanding of how stars and galaxies interact. And importantly, it offers a tool to map dark matter, which ties back into that big picture of understanding cosmic structure. As one NASA release said, studying these exiled stars could provide clues about the unseen mass shaping our galaxy. That unseen mass is the same dark matter that allows galaxies to form in the first place after the Big Bang. Having explored these diverse threads, from cosmic expansion to galaxy formation, from ancient stars to rogue stars, we are left at an inflection point in cosmic science. The evidence we've compiled is converging on one tantalizing message. Our standard cosmological picture, while broadly successful, is missing some crucial ingredients or twists. So, what do we do with this message? How do we reframe the foundations of cosmology in light of these findings? Rewriting the cosmic origin story. The time has come to face the profound implications of everything we've discussed. The foundations of cosmology, the Big Bang, cosmic inflation, the rise of the first stars and galaxies, the behavior of dark matter and dark energy, all of it may need refinement or bold revision. It's as if we've been reading a grand story but now discover hidden chapters that change the plot. One possibility is that our timeline of the universe needs stretching or flexing. Perhaps the universe is a bit older than 13.8 billion years. Not drastically, we're not talking double, but maybe the uncertainties allow for, say, 14 or 15 billion. If future data were to push that way, it might ease some tension. The Methuselah star would be comfortably younger, early galaxies a bit less extreme relative to age. However, adjusting age alone doesn't solve the core issues, because to make the universe older, one must adjust the expansion history, lower Hubble constant, or dynamic dark energy. And that adjustment must also fit the CMB and other constraints, which is non-trivial. So age tweaking within our existing model is limited. Another approach, new physics in the first billion years. We might introduce, for instance, a phase of turbocharged galaxy formation, maybe triggered by some exotic processes. For example, if dark matter particles had a small effective interaction, a dark force among themselves, they might clump quicker and help form stars sooner. Or if inflation left behind high-density ripples on small scales, mini-galaxies would collapse earlier. These wouldn't overturn Big Bang theory, but rather adorn it with extra complexity. The Hubble tension could be telling us something fundamental, like maybe the cosmic expansion rate changed more abruptly than smooth lambda CDM predicts. Some theorists propose a phenomenon called early dark energy, where a small fraction of the universe's energy was in a form that increased expansion rate for a while a few eons after the Big Bang, then decayed away. This could reconcile the differing expansion measurements. That idea adds an entirely new component to the cosmic recipe, beyond just dark matter and cosmological constant. It's a bit of reconning the cosmic script, sneaking in an extra scene to make the story flow consistently. If early dark energy or something similar is true, it's a crack in the standard LCDM model, lambda cold dark matter. LCDM has been our faithful guide, but it's always been phenomenological. We don't know what lambda, dark energy, really is, or what dark matter is. We've been fitting them to data. Now the data might be hinting at the next level. Maybe dark energy isn't constant, maybe dark matter isn't perfectly cold or collisionless, etc. Let's entertain a bigger picture scenario. Could it be that our concept of time since Big Bang isn't straightforward? In Einstein's relativity, time can flow differently in different conditions, but the Big Bang is usually considered a global time zero for our universe. However, some have speculated about whether the Big Bang was uniform or if some regions effectively started structure earlier. Unlikely in normal cosmology, but quantum fluctuations during inflation could, in principle, cause some patches to evolve slightly differently. There's even a hypothesis called varying speed of light, VSL, that attempts to solve some cosmological puzzles by saying maybe in the very early universe, light traveled much faster, which could mimic effects of inflation or alter early structure formation. If one were to go really far out, maybe the Big Bang itself was not a single event, but a transition that had some structure to it. E.g., a cycle. A previous universe collapsed partway, then bounced. The earliest black holes could be remnants from that previous phase, though no evidence for that currently, pure speculation. The idea of a cyclic universe or ekpyrotic universe where our Big Bang was a brain collision event sometimes naturally leads to thinking some seeds of structure could pass through from cycle to cycle. If something like that were true, again highly speculative, then indeed some objects could metaphorically be older than our Big Bang in the sense they originated before the hot Big Bang phase. Without going that far, another concept, the multiverse. If our universe is one bubble in a frothy multiverse, collisions between bubble universes could disturb initial conditions. It's been proposed that certain anomalies in the CMB might be evidence of such a collision, though evidence is tenuous. If our bubble collided with another, it might have triggered an early surge of structure or expansion in one region. But we're really grasping at straws there, and it complicates more than helps at this point. The more grounded takeaway is we are missing pieces in our cosmic puzzle. We have strong evidence the Big Bang happened, CMB, expansion, etc., but we clearly don't know everything about how that initial fireball turned into the universe we see. JWST and other new instruments are basically shining flashlights into the previously dark corners of cosmic history, and we're seeing unexpected shapes. From late science-style perspective, we can emphasize the dramatic turning point we're in. It's like being an explorer who thought they mapped the whole continent, only to find a vast new territory beyond a misty mountain. It's thrilling, but also a bit frightening, because it means rewriting textbooks, rethinking assumptions. We should underscore some key phrases. This shouldn't exist. We've used that for galaxies and stars that defy theory. What came next was worse, used to escalate from Hubble tension to galaxies to black holes. Prepare yourselves. We used in the opening to set the mood. Another common phrase is something like, "The true horror of what we're dealing with was in the transcript," in context of Hubble tension not being just a calibration error, but something fundamental. We might not need to use horror repeatedly, but we can definitely convey that unsettling sense that the universe might be ripping the rug out from under us. We should also reflect on the grand meaning. If stars and galaxies formed earlier and faster, maybe we, humans, life, could have appeared earlier in the cosmic timeline, given the right conditions elsewhere. Is it a coincidence that we see these things just as we have the tech to observe them? Not necessarily, it's just progress. But it does remind us that the universe might produce surprises quickly. One more thing. As a consequence of early heavy element production, since there were big galaxies churning stars early, the cosmos might have been enriched with the elements for life faster than we thought. That Guardian quote by Emma Chapman, "The Dark Ages may not have been so dark after all, and the universe may have been awash with star formation far earlier than we thought." If true, could planets and life have gotten a head start? Possibly trivial in time difference, but interesting to ponder. Life requires metals like carbon, oxygen, iron for planetary cores, etc., which come from stars. If those were around early, then maybe rocky planets could form earlier too. Not within the first 500 million years likely, but maybe by 1 to 2 billion years age of universe, some heavy elements were abundant enough. So from a philosophical angle, the timeline from Big Bang to potential life-friendly environments might be shorter than we assumed. The earliest life in the cosmos could have arisen when the universe was, say, 5 billion years old, just speculating, instead of, say, needing 8 to 10 billion. This doesn't directly bear on the age anomalies, but it's a ripple effect of early structure. Finally, the tone of closing should be one of cautious wonder. We set out to answer whether James Webb found stars older than the Big Bang. The cheeky answer is, not literally, but it found evidence that our understanding of the Big Bang timeline is flawed. It's as if those stars and galaxies are signaling that the Big Bang wasn't the whole story, at least not as straightforwardly told. Our narrative might conclude on the thought that the universe is both far stranger and more incredible. Each anomaly is not a roadblock, but an open door. The cosmos is inviting us to prepare for the unexpected, to let go of the comfortable notion that we've figured it out. When we peer through JWST or next-generation telescopes, we must be ready. The universe might throw out the script. It's possible in a decade we'll be talking about a new standard model of cosmology that includes things like early dark energy, maybe a revised theory of gravity on large scales, or a new particle that helped jumpstart structure formation, or an understanding that inflation had some wrinkles. In the most extreme case, we might one day find evidence that the Big Bang was just one chapter in a larger saga, say, hints of a time before time in gravitational waves or something. Then the phrase "older than the Big Bang" might take on a literal meaning in the context of a pre-Big Bang epoch. For now, it remains a provocative phrase capturing the feeling that some discoveries should not exist in our current worldview. And yet, they do exist. We have to account for them. In the journey of science, this is a pivotal moment, being confronted by evidence that feels paradoxical. Historically, such moments led to breakthroughs. Think the perihelion of Mercury's orbit. Classical physics couldn't explain, leading to Einstein's general relativity. Or the ultraviolet catastrophe, which birthed quantum mechanics. The Hubble tension and JWST's early galaxy surprises could be similar harbingers of a coming revolution in physics. That's exhilarating. It also means our cosmic origin story, how the universe went from a hot plasma to stars and galaxies, is getting a rewrite. The broad strokes remain: Big Bang, expansion, cooling, first atoms, first stars, galaxies, etc. But the details, those details, are far more intricate than the simple linear progression we once envisioned. We might add an analogy. It's like thinking you had a simple timeline of human history: Stone Age, Bronze Age, Iron Age, etc. and then discovering evidence of an advanced lost civilization that doesn't fit in that sequence. You'd have to revise history to insert that civilization or explain it. Likewise, we have to perhaps insert new epochs into cosmic history, e.g. the dark star epoch or the primordial quasar epoch, concepts that weren't in textbooks before. As we close, let's emphasize key late science vibe words. Fundamentally misunderstood the universe we already cited from Rees. This shouldn't be possible. We have implied that often. Unknown force tearing reality apart. Mention with Hubble tension we did via dark energy speculation. What remains is possibility we misunderstood reality. We did. Possibly a phrase like, the true horror is that we might be clueless about something basic. And maybe, final line, something like, the stars and galaxies have kept their secrets for eons. Now they challenge us to unravel a deeper truth, one that may require abandoning comfort and venturing into the unknown. The cosmos is beckoning us to revise our story of everything. The question is, are we ready to rewrite the origin of the universe itself? That would echo prepare yourselves vibe. Now let's incorporate any final citations appropriate in conclusion. Could use the Chapman quote as positive spin, early universe awash with stars earlier than thought, to confirm that statement about star formation far earlier. Or Leja's, upends settled science, we did already. Perhaps restate Rees's line or NASA line, like something woven into fabric of space we don't understand, implying new physics needed. Perhaps a good concluding cite is from NASA. There may be something woven into the fabric of space that we don't yet understand, which nicely encapsulates the vibe of cosmic mystery remaining. All right, time to write the final section in a cohesive, dramatic way. The evidence is now undeniable. We are missing pieces of the universe's origin story. Every anomaly we've explored, the conflicting expansion rates, the gargantuan infant galaxies, the overgrown early black holes, the ancient stars on the edge of time, all of them point toward a single, staggering conclusion. Our fundamental understanding of cosmology is either incomplete or deeply flawed. The Big Bang Theory remains robust, but it's clear that the cosmic timeline built atop it needs revision. It's as if we've been reading a familiar book and suddenly new chapters have appeared, chapters that shouldn't be there, yet undeniably are. What might those chapters say? They could tell of a universe that forged stars and galaxies at breakneck speed, far faster than our standard physics allows. They might hint that the expansion of space itself had quirks, perhaps an early turbo boost, an unforeseen surge of dark energy, or a wrinkle in gravity. They may whisper of exotic forces or particles, dark matter behaving in unexpected ways to seed black holes, or stellar engines fueled by dark matter annihilation lighting up the cosmic dawn. In essence, these new chapters would force us to accept that the neat, tidy timeline from the Big Bang to galaxies is too simplistic. Picture the Big Bang as a dramatic opening act, the universe's birth in fire. We thought the next acts were understood. Cooling, primordial atoms, gradual coalescence into stars, then galaxies, then clusters, and so on. A slow progression like cosmic childhood to adolescence to maturity. But now we're finding characters in the story who appear far too early, like a child prodigy who shows up in Chapter 1 with the abilities of an adult. We have galaxies in the universe's infancy that behave like they've been around for eons. We have black holes in the first chapters that ordinarily shouldn't appear until the middle of the book. Something caused these characters to evolve at warp speed, and we don't yet know what that something is. It could be that we need to add a new ingredient to our cosmological recipe, not just dark matter and dark energy, but perhaps a new kind of field or a variant form of dark energy that acted early on. Or maybe the ingredient is already in the recipe but misbehaving, Perhaps dark matter interacts with itself slightly, causing more rapid collapse of matter in those early years. Possibly, the speed limit for star formation isn't as strict under pristine conditions. The first stars might form in a frenzy, and their deaths trigger an avalanche of early star birth. The truth is, we don't have the full answer yet. We are, as of this moment, standing on the brink of discovery, peering into a darkness that JWST has only begun to illuminate. And what about that most tantalizing question of all? Could something be older than the Big Bang? So far, all evidence still places the Big Bang as the beginning of our universe's time. But the fact that we even entertained the notion speaks volumes. If one day we find concrete evidence that, say, a black hole or a pattern in the cosmic radiation indicates activity from before the Big Bang, it would shake physics to its core. Some theories, like cyclic cosmologies or multiverse collisions, suggest that our Big Bang might not have been the absolute beginning, that perhaps there was a before. It remains speculative. Yet, when we find stars like HD 140283 that nearly outage the universe, or when our calculations of cosmic expansion hint that the universe might be a touch older than we think, it certainly makes us wonder, have we truly captured the full timeline, or is our 13.8 billion year clock missing some ticks? Even without invoking a pre-Big Bang era, the challenges at hand are monumental. We may have to rewrite the standard model of cosmology to include a host of new phenomena. The coming years will see cosmologists test ideas like early dark energy, variable fundamental constants, and other exotic tweaks to see if the Hubble tension can be resolved without breaking everything else. Particle physicists will ponder if a new particle, maybe a fourth neutrino type, or a dark sector force, could explain why the early universe pumped out structure so efficiently. The James Webb Telescope will continue to hunt for the first light of the universe. Perhaps it will spot a population 3 supernova or pin down the masses of those impossible galaxies with spectroscopy, confirming just how heavy they truly are. We might yet discover a galaxy at redshift 15 or 20, only 200 million years after the Big Bang, shining in Webb's images, which would further press the question, how did it get so big so fast? Each new discovery is like tightening a vice on our old theories, forcing them to either adapt or shatter. Let's not forget the emotional dimension of this scientific drama. For scientists, it is equal parts thrilling and terrifying. On one hand, what a time to be alive and studying the cosmos, to witness what might be the cracks that lead to a new paradigm. It's the kind of once-in-a-generation opportunity that could lead to the next Einstein-level breakthrough. On the other hand, there's a sense of existential dread. What if the universe is not only queerer than we suppose, but queerer than we can suppose? What if our human brains, bound by experience and intuition, struggle to comprehend the true mechanisms at play? When we say there may be something woven into the fabric of space that we don't yet understand, it is both a promise of discovery and a warning of our current ignorance. From the perspective of the late science narrative, we might say, the universe has pulled the rug out from under us, and we're left floating in a void of uncertainty and wonder. But this void is exactly where new knowledge is born. Every great advance in understanding came from recognizing a seeing. We are at that precipice now. The cosmology of 2030 or 2040 may look very different from that of 2020. Students in the future might learn about the Hubble crisis and how it was resolved by the discovery of XYZ. Fill in the blank with whatever new physics is found. They might learn that in the year 2025, astronomers using JWST and other tools uncovered the first evidence that, insert groundbreaking concept here, and that changed our cosmic origin story forever. Imagine a future where we identify exactly what caused those galaxies to bloom so early. Say we discover a new property of gravity at small scales that makes matter clump faster in the early universe. Effectively a tweak to general relativity. That would be Nobel-worthy, and it would revolutionize the expansion and structure growth. Or perhaps we'll confirm the existence of dark stars, proving cosmograph can ignite stellar-like objects. That would not only be a shock to stellar astrophysics, but would also finally give us a clue to the nature of dark matter, since we'd be directly seeing its effects beyond gravity. If dark stars are real, then some of the galaxies Webb sees might not be galaxies at all, but single soup-arounding thought. Or consider if we solve the black hole growth riddle by discovering a whole population of intermediate-mass black holes in dwarf galaxies that merged early. That might mean the universe had a period of hyperactive mergers that current simulations haven't captured. We might have to rewrite the timeline to insert a quasar nursery epoch much earlier than anticipated. Then there's the Big Bang itself. Right now, the Big Bang model stands strong, but it has its own puzzles, like what caused inflation, what came before inflation, etc. The more we learn about the first stars and galaxies, the more constraints and clues we actually gather about those very primordial moments. For instance, if we find that structure formed too efficiently, maybe it hints the initial fluctuations from inflation had a certain spectrum, maybe a blue tilt with more power on small scales. That feeds back into inflation theory, potentially narrowing down which inflationary models among dozens could be correct. It's all connected. Solving the mystery of early stars might also illuminate the mystery of the universe's first trillionth of a second. We started with a provocative title. James Webb found stars that are older than the Big Bang. In the end, what we found is perhaps even more wondrous. Evidence that forces us to rethink the very notions of cosmic age and cosmic timeline. The stars aren't literally older than the universe, but they act as if they came from a universe where the rules were different, a universe that shouldn't exist, yet somehow did. It's almost as if JWST, with its infrared eyes, warps space, but into a different version of the universe, one that our theories didn't predict. Of course, it's the same universe, but it's telling us it has facets we never anticipated. So where do we go from here? We embrace the unknown. We let these impossible observations guide us towards physics. We design new observations, more JWST deep fields, upcoming missions like the Nancy Grace Roman Telescope and Euclid, which will map galaxies and dark matter with precision. Next-generation observatories that might catch the very first stars in the act of forming, or detect gravitational waves from the depths of the first massive stars. The journey is just beginning. A century ago, we didn't even know other galaxies existed. Now, we're dissecting the universe when it was a toddler. What will we know a century from today? One thing is the universe is not afraid to contradict us. When our hubris grows, the cosmos has a way of smashing our expectations. It happened with Copernicus dethroning Earth as center. It happened with Hubble and expanding universe. It happened with the discovery of dark energy accelerating the expansion. Each time, we were forced to humbly revise our view. Now it's happening again. It's as if the cosmos is saying, brace yourselves, the truth is even stranger than you thought. This shouldn't exist, and yet it does. We find ourselves repeating that refrain. But in that contradiction lies the key to progress. By confronting the data head-on, by saying, all right, the universe has dealt us a paradox, let's solve it, we are embarking on perhaps the most exciting chapter of cosmic exploration in decades. The foundations of cosmology are being shaken, but not broken, at least not yet. We're testing their resilience. If and when they give way, something new will be built in their place, raising it more encompassing. Perhaps in a few years, we'll speak of a post-LCDM cosmology, one that includes early dark energy or variable constants or what have you, which elegantly explains Webb's findings while preserving all the successes of the old model. Perhaps we'll celebrate how the Webb anomalies ushered in a new era of discovery. For now, we must live with the tension. the cognitive dissonance of seeing stars that shouldn't exist and galaxies that defy their age. It's a bit unsettling, like realizing the ground you stand on might be shifting. But it's also beautiful, nature in its deepest form, inviting us to solve its riddles. The universe has handed us pieces that don't obviously fit, meaning the way we've been trying to assemble it needs to change. In the end, James Webb didn't quite find stars older than the Big Bang, but it found something perhaps far more important. It found the limitations of our knowledge, written in the light of ancient stars. It found the pressure points in our understanding where new truths are waiting to burst forth. And in doing so, it has effectively reframed the questions. No longer can we ask, how did the first stars form, in the comfortable expectation that the answer is gradually, according to established theory. Now we must ask, how in the world did the universe light up so fast, so early, with so much? And that question demands creativity, daring, and open-mindedness to answer. So as we conclude this journey, we circle back to the beginning. The stars and galaxies we observe are messengers from the dawn of time, telling us a story we hadn't fully heard before, a story of a young universe that was more alive, more fiery, more hurried than we ever imagined. We thought we understood, but what came next in our observations was a twist that left us reeling. We have no choice but to rewrite parts of. Keep your eyes on the heavens, because the cosmic saga is ongoing. With each new discovery, we inch closer to the underlying truth of our reality. It may unsettle us, it may thrill us, likely both, but it's the path we must take to truly know our cosmos. In the quiet of a starry night, if you gaze up and feel a slight shiver, perhaps it's the realization that somewhere out there, in the ancient darkness, lies the answer that will resolve these paradoxes. The universe is waiting for us to find it. Prepare yourselves. The age of cosmic discovery is just getting started, and everything we think we know might yet change. The stars have not finished speaking. We must be ready to listen, no matter how surprising their message. This is not the end of cosmology. It is a new beginning.